Great.
Can you unmute me? It's not letting me unmute.
No, but we can hear you talking about the problems.
Oh, you can? Okay, that sounds great. Even better. All right, well, we'll see how this goes. Hello, everyone. I'm Daniel Allen. I'm the PI of the Drivers RCN, which Adam just presented some of our work from. I'm going to be talking about two.
Oh, now you're on mute. You've managed to mute. Somebody's muted you, man. Sorry. You're the only person who can unmute yourself.
Let me try this.
There we go. Onwards.
Oh, wait. Am I still muted or am I good?
No, you're fine. Oh, you managed to stop sharing your screen, though. Dan, come on.
Not used to Teams. I'm sorry. Okay, so
oh yeah, brilliant. Carry on.
all right, there we go. So I really don't need to convince this crowd why we should care about these non-perennial streams, but we do note that they're widespread. They provide many ecosystem services, and they're flowing in dry stages, and they're also becoming more common for a variety of reasons in a number of places. But more broadly, as Adam was saying, the non-perennial flow regimes are globally understudied, largely due to a lack of global scale coverage in our gauging station network. The location of gauges on streams that dry is not very well distributed relative to those that do always flow. And then finally, hydrologic models, we might be able to use them, but they tend to overestimate low flows. So here I'm going to talk about two different projects where we ask two different questions. The first being, how do these non-perennial flow regimes vary spatially across the continental United States? And then the second is, how might these be changing over time? And so we use the same data set that Adam was talking about, with 540 USGS gauges with 10 years or more of data that experienced drying. 152 of these were reference locations, meaning that they are in pristine watersheds where human impacts are minimal. 388 are what we call non-reference, where those flow regimes are impacted by humans in some way. And so we calculated three different drying metrics. This is a little bit different than what Adam just talked about. This is the same, the duration of the annual no-flow days. We did calculate the rate a little bit differently. Instead of, for here, this is just the days of the peak to the no-flow. And then in this project, we also looked at the timing of the no-flow day, the first no-flow day throughout the year. So when we look at the spatial variability, I've got a map here. At the top is the no-flow fraction, or just the amount of time of the year the stream went dry. Reddish, yellowish hues are more. We found that they were generally greater in the south and the western United States. We looked at timing. Again, we see some spatial patterning where we have red and yellow being earlier timing, and that's earlier in the west and the south. And then finally, when we looked at the peak to no flow or that rate, we didn't see quite as clear spatial patterning throughout the United States. One thing we wanted to do is we wanted to compare the differences between the reference and non-reference gauges to look at the effects of human impacts on these flows. And so one thing we found was that the no-flow fraction was largely unaffected, except for in this western desert region, but we only had 7 reference gauges there, so take that with a grain of salt. However, when we looked at the timing, we did see some impacts of the human footprint on the timing, where in eastern forests, the dry down tended to be earlier, and then we found the opposite in the western desert region. And then finally, when we looked at peak to no flow, we saw in especially 2 regions, Mediterranean California and the southern Great Plains, that with streams with human modifications were drying out more quickly than those with unmodified streams. And so much like Adam just talked about, we use this random forest modeling approach to look at what variables might be driving some of these differences. And so here I've got this is just from top to bottom, a list of the different variables that we put into that model in 4 different categories: topography, land cover, human alteration, and climate. Here we have our 3 metrics: no flow fraction, first no flow, and peak to no flow. I'm not sure if you can actually see my mouse or not, but what we see is if you look at the size of these circles, it indicates the importance of the variable. And so as you go left to right from these rows of column, that's no flow fraction, first no flow, peak to no flow, and then to give an indication of the direction of that effect, we change the color so that negative values are more yellow, positive values are more black. And basically what we see is largely across all of these 3 categories, precipitation to potential evapotranspiration ratio is really important. So climate was a major driver of these, especially for the no flow fraction and first to no flow. That's probably why we saw this geographic patterning. But for the peak to no flow, we saw that many different variables were sort of equally important. And so what that tells us is that this dry down rate is something that is less driven by climate and more driven by local watershed factors. So to sum up, we found greater no flow duration in the southern and western US, earlier no flow timing in the western US. The dry down rate did not have spatial patterns. Streams with human influences can dry down faster and can have different no-flow timing than reference streams. And so this brings us to the second part of our talk, which is how are these changing? So again, we use the same data set, except this time, so we calculated these metrics annually for each gauge, and we use something called the Mann-Kendall trend test to look at if there was a change at an individual gauge. Then again, we use random forest models to investigate the drivers of what might be driving these changes. And so again, sort of 3 maps, but this is a little bit different. Here, each gauge is plotted with a color, and if it's red, that indicates that we're having significant drying. If it's blue, then that indicates that it's wetting. And so interestingly, what we're seeing across all of these gauges is significant trends in the changes of duration at 40%. So 40% of these gauges are showing changes in the amount of time a stream dries. 26% of that is drying. Again, we see more spatial patterning here. We're sort of in the southern half of the US. We're seeing a lot of that drying. And interestingly, in sort of the upper Midwestern part of the United States, we're seeing an increase in wetting. When we look at timing, the changes are not quite as dramatic. We see trends at 14% of the gauges. 11% of that is earlier, again, mostly in the southern US. And then rate, we see significant trends at 15% of the gauges. And again, sort of, it's not really a clear pattern here with the drying rate. But across all of these 3 metrics, 50% of the gauges have significant trends in at least one of these metrics. So we're seeing widespread change in how these non-perennial streams in the US are drying. Similar to the plots that Adam showed, this is another way to visualize the results of the random forest models, where for each variable we have a list of the most important variables from top to bottom and sort of categorize them by color here. And so for no-flow days, what we see in terms of what's driving the change is the precipitation to potential evapotranspiration ratio of the prior year. And so that's sort of suggesting that the dryness of the prior year is indicating what's happening in next year. And then physiographic variables were also important, things like drainage area and bedrock depth. With peak to no flow, that dry down rate, we saw something a little bit different. Here, we're seeing sort of land and water use variables pop in to be more important, things like the amount of wetland, the amount of forest, physiography as well. And then the timing of the first no-flow day, we're seeing is driven largely by climate and also largely by those climate variables from the prior year. So really what this is showing is that for both of these, for 2 of these variables, no-flow days and or the duration of the drying event and the timing and when that starts, that the antecedent conditions, the prior climate years, are really critical. So to sum up this part of the talk, 50% of these gauges have a significant trend in at least one of these no-flow metrics. Trends in no-flow duration are most widespread. Drying is earlier in the south and longer, but then also later and for shorter periods in the north. And then the relative importance of climate and land use and physiography varies by metric. Duration is a function of climate and physiography. Rate is more of a is a function of land use and physiography, where timing is more of a function of prior year climate. And so because of the importance of land use on drying rate, that's likely in both of these projects what is leading us to find less of a spatial coherent spatial pattern for those two metrics. So with that, I'll take questions.